Hello and welcome to the program. I'm Carl Pauls. I'm here with Gabe Ignetti and our special guest, Robert Steinhaus. Robert Steinhaus is a retired engineering staff member with Lawrence Livermore National Laboratory. He has degrees in biological science and engineering physics. He's worked at the Environmental Science Division studying the effects of and has been involved in engineering for the atmospheric nuclear tests performed at the Nevada test site. He's done environmental research on the Marshall Island test site locations as well. He's worked in other areas of research, including his research on magnetic and inertial fusion energy power plant technology and molten salt fission power plant on the thorium cycle. Welcome to the program, Robert.
Well, great to be here. Thank you.
So you were sort of telling us a moment ago about the real authorities and the people you work with at the Lawrence Livermore Lab, and tell us a little bit more about that.
All right. Well, the truth of the matter is, and it will come out quickly, is that for most of my 30-year career at Lawrence Livermore National Lab, I really worked for better men, wiser men, more intelligent men than myself. I was a trusted member of a physics engineering team, but there were a lot of guys that were exceptional talents, and Dr. Ralph Moore is one of them. Obviously, Edward Teller was one of them, but there are a lot of, you could go down the hallways in the engineering building and just find some exceptional talents. So I was just lucky to be part of that team. And I would probably characterize myself, and I think most of my team members would also say, this guy was, he was nice, but he was a little guy. He was just a little guy. So as long as you want to listen to a little guy, I'm a little guy that's happy to talk to you about lots of wonderful experiences at the laboratory.
I think that sometimes that's the best we can get, and you know what? I'm perfectly happy. I'm in a similar position. I'm there in my current job as a support role, supporting a fantastic project, and working with really important people in the field. So I appreciate that position. So I'll get right into the questions. Having been involved in atomic testing, is there any thought in your mind of whether or not humanity as a whole would survive a nuclear war, and how real is the danger of nuclear war?
Well, luckily, we haven't had a nuclear war since the two devices were dropped on Japan to end a very terrible conventional war back in 1945. So, in a certain sense, from an experimental standpoint, no one knows exactly how bad a full exchange nuclear war would be. It would be terrible. I mean, I think there's little doubt of that. My own estimate, based on discussions with people within engineering department at Lawrence Livermore, something like 7 out of 10 people, you know, now living on the planet would die within 4 years of a full nuclear exchange. And the majority of the people who would die would not be from radiological problems, although there'd be plenty of those in the initial couple days after the event. But most people would die from other things related to food distribution, actual starvation, breakdown of order. Those things would actually kill more people overall than the actual blast effects of a full nuclear exchange. So let us all pray that we don't have to go through that. I'm actually shocked right now how people seem to be thinking about nuclear war from the standpoint of potentially like riding through it and having it as a potential experience. It doesn't seem like our leaders really fear the prospect of nuclear war the way they once did. They're
Hmm.
willing to say, well,
Mm.
don't let yourself be intimidated by the prospect of nuclear war. It's just another thing. We'll roll it into planning for the next election, somehow.
Ah.
And boy, that is not the case. I can absolutely tell you as a team member that field tested, you know, many, many dozens of weapons. They work and they are terrible in their
Yeah.
impact. And I just pray that they will never be used. And the whole idea, and we really believed it in field tests. Maybe you will say that we were just shielding our hearts or something, but we really believe that what we're doing in field test would deter war. That was the whole justification. It was never as like a first strike potential to knock out quickly, like major industrial or competitors like Russia or China or something like that with a secret first strike. That was never a consideration. It was all just to provide the credibility to deter war. That was what the guys in the trenches were thinking about, most of the time, not anything else.
Hmm.
So I'm just hoping that we come to our senses and we realize how serious a nuclear war would be. Certainly the 7 out of 10 is worldwide. It would be much more intense in localized areas, that were targets. So in those areas, it could be very, very, very high, casualties. And these are terrible things to talk about.
It could knock out the ozone layer or seriously damage it, very seriously.
Well, there are speculations like that. Also, nuclear winter has been frequently discussed. I I personally think that these effects are not quite as they're proposed in the public press, or at least I remain unconvinced that there are major effects. I just have not studied those phenomena to the point where I'm comfortable in coming out and saying, yes, nuclear winter would actually kill everyone on the planet and all life. There are people that argue like that. I think that 7 out of 10, and with more people probably surviving in the southern hemisphere than in the northern hemisphere. I think that those are my own studies.
Maybe you could answer this, have an environmental background, but would the ozone layer, even if it was seriously, seriously damaged, would it heal itself?
Well, I think so. In fact, almost all phenomena that we observe on the planet, every time mankind disturbs the natural environment, there is a process of recovery. And things like Chernobyl, for example, people were claiming, well, that won't be anything that people can inhabit for 1,000 years. It'll be complete devastation, forever. And other nuclear accidents have similarly been posted or suggested in that way. And I think that is just an emotional overstatement, and it just hasn't been borne out by the facts. So while there probably is an impact on the ozone, I don't think it's a principal effect, or at least I don't understand the mechanism for how it could be a catastrophic destruction of the ozone layer. Uh, we have a kind of delicate ozone layer as it is, as a result of various chemical pollutants and things like that we've released over the years. That actually has improved, over recent decades. But it's not to say that the ozone layer isn't already challenged by what we do. And I'm sure a nuclear war would be a significant challenge to all of the ecosystem, and the ozone layer is probably part of it. I think that Hollywood has kind of participated in creating these false images of total destruction. It's just not borne out by the facts. A single weapon would probably kill something on the order of 60,000 to 100,000 people, depending on yield and where it was delivered. If you deliver it into an urban area, it could certainly create havoc. And there's just no doubt the technology that we worked on back in the Cold War could, in the wrong hands with the wrong leadership, really lead to a terrible prospect, a great loss of life.
Right.
And we just need new leadership. If the current leadership doesn't respect uh, the potential for loss, I mean, just horrendous loss. Even a single weapon exploded in a major port like Los Angeles port. If you snuck a weapon into a transport container, even a single device like that, it's estimated by the laboratory to drop the GDP for the United States by 75%. So you would have
Whoa.
25% remaining, and that's a huge number of jobs. That's a huge reduction in prosperity and potential. So, even a single weapon properly placed, and it wouldn't even have to be a good weapon. In field tests, we would try to get consistent high yields from all our devices. And the truth is, you can have a very high economic impact device that is not high yield, that doesn't create a huge explosion, but which does sort of fizzle or splatter fission products and nuclear materials over a wide area. If that area happens to be something like a stock exchange or a major marine port, commercial port, you can really have a tremendous economic impact on the country.
Mhm.
And while that's understood, I don't think it's really, people haven't acted on it. Homeland Security has some provisions, but I would not trust the amount of effort that's gone in so far. As 20 years ago, there were promises made regarding doing cargo container searches and cargo container scans. And the technology to do that was supposed to be developed, within 5 years of the legislation to protect the ports. And it, that scanning technology was never successfully developed.
Mm.
So we really are operating depending on foreign ports, essentially, that have their ships and ship material to the United States. We depend on them doing our nuclear security for us. We don't do the nuclear security ourselves in a responsible way. So if a foreign enemy wanted to ship a container to France and then that container gets reshipped to the United States, uh, there isn't enough provision in our preparations to prevent a serious nuclear accident.
I want to take a tangent on this. I've seen James Conca, who works in geology and waste management, talk about the sort of the idea that a dirty bomb, that a conventional explosive with fission products like cesium are not incredibly effective. They're not nearly as effective as a conventional weapon in causing the spread of radiological contaminants and causing this drop in GDP. What's sort of your idea of, like, if you had something like a so-called dirty bomb with just all of the cesium that you could gather up from medical devices or otherwise, is that going to cause even a fraction of the chaos that a conventional weapon would?
Well, once again, we don't know from an experimental standpoint. And a lot of my work at the laboratory was experimental and field
Mhm.
testing and things like that. So I always hold projections based on computer models and things like that as a secondary source of in importance. It's always nice to have direct data.
Right.
But in terrible radiological disasters, you don't want to have direct data draw from. You would prefer the computer models by far. And I think the fear around dirty bombs has been overplayed. I would agree that they are not as significant issue at all as a conventional nuclear weapon. What is probably underappreciated is that you can form critical masses of fissile materials down to about 6% enrichment. Normally, people don't think that you can get a bomb out of 6% material, which is only a little bit more enriched over low enrichment uranium. But with a 6% enrichment device, it's a huge physical device, and it does not typically go off in a way that produces high yield. It produces what's called a fizzle event. And fizzle event is significant from a economic standpoint, not from a military standpoint. Fissile event will produce huge amounts of contamination that splatters an area of a couple square miles, perhaps. That's probably what you would see from a non-professionally prepared device. But
That's pretty big.
it is, it is. Well, we actually did have fizzle type devices that we tested at the Nevada test site. There is a section of the test site called GMX, or GMX was actually the name of a series of tests, not just one test. But they were all tests made by Lanel, our kind of national laboratory competitor, friendly competitor. They were trying to set the boundaries on design for new devices, especially small devices. So they built a whole bunch of special little devices that we tested just to see what are the limits of design. What can we, how far can we push parameters before things stop working, and to what degree? And so we would get these devices that were marginal, that wouldn't produce high yield, that would just splatter over the surface of the desert. And it turns out now that the parts of the test site that are today, now 50 years after all of this testing, the parts that are the most radiologically contaminated are those fissile event sites. It's very hard to clean them up. Nuclear materials get resuspended by winds and dust devils and all kinds of things like that. And the end result is a fissile device is actually not an inconsequential weapon, and it is a more serious weapon if it's delivered into an economically significant area than a dirty bomb. A dirty bomb, relatively speaking, anything that I've seen conceptualized, a dirty bomb would not be nearly as significant as a large 2,000 pound, 6% enrichment fissile type bomb.
Something like the atomic bomb at Hiroshima and Nagasaki.
No, this would be much larger in size and weight, so it could not be delivered by a missile or even an airplane, probably. You would have to haul it in on a barge or put it inside of a ship, something like that. If a country were willing to devote resources to it, it could have tremendous economic impact on the United States or any Western country. But that's something I hope doesn't happen. And
Yeah,
that is, however, a significant concern that's not really properly addressed
Yeah.
currently, in my
yeah.
opinion.
Yeah. Very interesting. Well, let me get back to our main line of questioning. What is your opinion about the relationship between attaining atomic energy and the problem of the actual proliferation of nuclear weapons and other hazards that we've been discussing?
Wow, that's a big one. And I'm probably not the world's best person to ask about it. I was close to the technology, for making weapons and testing weapons. Actually, I'm a nuclear tester. I'm not a nuclear weapons designer. I I would mostly take things that other smarter, braver, more better men would dream up, and then I would just take them out to the field and try to figure out if they're going to work and whether we could make them work. And so obviously, nuclear energy can do a tremendous amount of good if it is applied in the right way and used for doing things like producing commercial electricity, which is something that all societies, all modern societies need. Uh, it can do tremendous harm if it gets involved in war and involves exchange of weapons. Horrific amounts of harm are possible. So, there are good men that have taken either side of it. As part of Lawrence Livermore National Laboratory, I made it my policy that if ever I had a tendency to take an opinion other than the opinion, well, other than the announced opinion of Edward Teller, I would sit on my hands for 10 minutes and wait before I would type anything or say anything. And I tend to come down on Teller's side, on most of the arguments. And Teller had very excellent opponents in people like Hans Bethe and other men who focused more on the potential for harm and the need to reduce the chance of proliferation. And Tyler was more interested in making sure that we could match the Soviets, just technical development by technical development. And he did believe in the kind of intimidation of uh, using nuclear weapons as a means of keeping the peace, but through strength, through matching, the Russians in every technical development, and in some cases trying to be ahead of them, but at least matching them, in capability.
Right. Well,
Yeah.
I got a question here. I mean, if you have a nation and they start a nuclear power program, aren't they building up the brain power, the expertise to make them more capable of building a nuclear weapon if they decide to?
Yeah, there's a tremendous amount of material actually available out on the internet and elsewhere, that allows you to get a pretty good sketch of a nuclear weapon. At the laboratory, we had a summer student that we hired, a physics summer student that we assigned him the summer project of designing a nuclear weapon, just based on review of unclassified things he could find on the internet and elsewhere. And after 3 months, our weapons designers looked at what he had actually devised. And this was a good student, a good physics student, at he's just graduating from undergraduate, levels of education in physics. And
But not nuclear physics, just
no,
physics.
just physics. But
Yeah.
he was
Okay.
skillful, and he was chosen by the laboratory initially to do other things. But they wanted to see, how good, or how easily, he could design a nuclear weapon. And the opinion of the senior weapons designers at Lawrence Livermore National Lab was that the weapon he devised would almost surely work. It would be a
Hmm.
little question of, would it be absolutely the maximum yield? Probably not. Would it be the absolute maximum reliability? Probably not. But just a good, underclassman, physics student, mm, they felt was good enough to provide a workable design, something that would actually, you know, have some yield to it.
Hmm.
And so, uh,
Interesting.
yeah, that was interesting and kind of scary in a certain respect.
Yeah. Yeah.
The technology has not been, I mean, what really keeps people from building weapons these days is lack of access to the nuclear material, to the high purity nuclear material. If the nuclear material by any means was made more widely available, then the potential for misuse of nuclear would be far higher, and our lives would be different. We would have much scarier and more troubled lives
Hmm.
if it were easier to get nuclear materials.
So
I,
I get,
I pers-
go ahead.
yeah. Oh, well, so I'm in favor of non-proliferation, uh,
Oh,
surely non-proliferation efforts, but I'm not entirely confident that the way that we currently try to curtail access to nuclear materials will hold up in the long run. I think things like thorium fuel cycle and lifters and thorium molten salt reactors, all of those are great, wonderful things that will, if handled the right way, benefit mankind. It is also true that thorium and U-233, in my opinion, is a better fuel cycle actually for producing a small number of defensive weapons than
Mhm.
plutonium or the other technologies that were, devised following the Second World War.
Wow.
Yeah, I do worry a little bit about proliferation with respect to the thorium fuel cycle, which I'm a great proponent of thorium, and I love lifters. You know, I would like to see them build in the thousands of reactors, but there is a real risk. There is a risk that if these reactors weren't properly inspected and looked after by, and IAEA inspectors, there would be the potential for diversion of bred U-233 into weapons.
How about just spent fuel from a regular standard nuclear reactors? Could that be turned into weapon fuel or
Yes,
weapon material?
right. Well, that's a question for nuclear designers in the end, not weapons testers. But I will say that the two most senior weapons designers in the weapons complex, that's Richard Garwin and Carson Marks. Uh, those guys felt that reactor grade plutonium was a potential weapons material. They absolutely felt with the right design techniques, they could make high yield, high reliability weapons out of reactor grade plutonium. Their feeling was that there was not safety in the rules of thumb, of the isotopic
Mhm.
contaminants. It's not enough to just say, well, I have 10%, plutonium 240 contamination in this material, so it can't be used for weapons.
Mm.
And, senior designers like Richard Garwin, who is an actual genius, I mean, just flat out. He was the actual lead designer of the hydrogen bomb at uh, Lionel. We provided some input from Lawrence Livermore, but that was a Lionel project, the first one. And the truth is that the senior designers feel that there is no grade of plutonium that really is entirely safe if you use the right design approach, you know. And I have to bow to them and accept their opinion. They've actually written papers to that effect. The problems with the papers is that the papers had to go through a security process, and the security process unfortunately said, well, we'll let that paragraph go through, but this paragraph we have to cut. And the end result is that the papers written by the senior designers end up kind of choppy and sort of jumps in the argument is what it amounts to. And it's all the result of the derivative classifiers who reviewed those papers and said, this goes, this doesn't. So I just want to warn people, if you read papers by Carson Marks and Richard Garwin on this topic, their opinions are very clear. Unfortunately, their arguments are not always as clear or as it's detectable that there is loss in the paper as regards to the consistency of the argument as a result of the impact of derivative classifiers
Mhm.
that we're looking at the security aspects.
Well, following up on the molten salt reactor as being used to produce weapons, that's something that is almost intuitive. You could have a chemical kidney that's going to scrub out the contaminants that make your reactor worse. But it could also be used to pull out useful isotopes in terms of producing a weapon. Is that the fair estimate? And the U-235, U-233, and the other isotope mixtures, those aren't insurmountable problems. Is that what I'm getting from you?
Yeah, there's certainly not. There are problems that are presented by the thorium fuel cycle, for example, with respect to weapons use. It's not as direct and straightforward in terms of traditional weapon design, but all those problems are things that can be overcome. We can engineer out any limitations such that it is not safe to say that U-233 or even fertile thorium, actually, can't be used as a weapon. Thorium can increase the yield of a device by 30 to 50%.
Wow. Yeah. And we have a black market too.
Right. Well, there is the potential of it. At least there's an agency called NNSA that looks after nuclear security. And those guys do actually go around the world looking to try to find and collect nuclear fissile materials. And they actually have teams that are trained to make incursions and, if necessary, by force, to acquire all of the fissile materials that they can find and locate. The guys will try to track you down and they will try to find you. And they are tough. They are tough. You guys really are better off. Try to do a fusion experiment, build a fuser or something like that. Nobody's complaining about you doing fusion. If you try to do anything with fissile materials, the guys at NNSA will come around and make your life miserable.
Yeah.
The truth is that all thorium devices, practical devices, are actually uranium devices. They just use a different isotope of uranium, U-233 instead of U-235. And hoping that that little change is enough to change the picture dramatically is not really hoping for anything in reality. At the Lawrence Livermore Lab, our senior designers actually did a review when talking to Hanford, who was a traditional supplier of fissile materials, high purity fissile materials for the United States. And the senior designers said in a actually unclassified document that U-233 is not only a good, weapons material, it is an excellent, weapons material. And it's possible that even simpler kinds of designs for U-233 are possible. We didn't get a chance in test program to really test full, complete U-233 devices.
He did have Teapot Dome, but I guess that
We
was,
did. We
yeah,
did,
that
and
was, yeah.
that was a combination of a U-233 component in a plutonium design. And that was low yield. It did work, but it produced a low yield event. And we never tested a completely U-233 device ourselves. U.S. Field test never did that. The Indians did have a Smiling Buddha test in the 1990s, and there is said to have been a very, very small pure U-233 device that was successfully tested. But I don't know a lot of details about that test.
Hmm.
So and this is a little diversion from where we were before. You said that the availability of fissile material or weapons potential material was probably the biggest risk out there. So I was talking to a nuclear engineer who is a really big fan of laser enrichment and laser separation. And the criticism of that technology is it makes enrichment too cheap and too efficient. Is there such a risk that, we can lower the cost of producing highly or even, reactor grade uranium to such a level that it becomes much more difficult to detect and much easier to produce this material?
Yeah, there's concerns there, and they have been recognized within, the weapons establishment. Frankly, I think NNSA and others are not anxious to talk about the liability of laser enrichment and what it potentially could mean to the approaches that we have leaned on for 50 years, to try to control the spread of nuclear weapons. Um, I think they're actually hoping that people sort of forget about laser enrichment. We had several commercial laser enrichment projects underway 10 years ago, and those have not really resulted in commercial technology. I don't know all the ins and outs of it, whether it was just a technical failure or whether actually there was some influence from NNSA or others responsible for nuclear security to basically shut down that technology, to not fund it, to in what ways as could be found, to discourage it. I I know that we had a program called Avalis at Lawrence Livermore Laboratory, which was in fact a form of uranium enrichment. That was the intention of Avalis, is to use lasers to enrich uranium, and it was a successful project. We were able to use uh, large lasers to do that job. The level of enrichment that was achieved was not weapons grade. It was kind of mid-grade material that they were able to produce, but it also wasn't a multi-pass kind of
Hmm.
system. It's possible that using the Avalis technology to do half of the work and then sort of some refined laser capability to do the back half of the work, you could get all the way to uh, weapons grade material uh, with laser enrichment. And once again, that program didn't go beyond a certain point. I think what was basically proven is that yes, that is possible. It's possible to use lasers to do laser enrichment and
Hmm.
to, in fact, sort things like fission products from fissile and to come out with just what you want.
Hmm.
Some of the peaceful sides of it are that, there are lots of things in fission products that are valuable. You get valuable elements in there. And if you were able to purify using laser technology, laser separation technology, you could produce, valuable secondary, revenue stream from the nuclear fission that you're doing in molten salt reactors.
Like what?
Well, there are a lot of materials like rhodium, and there are things that are far more rare than gold. Special materials that we normally just throw away because
Right.
they're mixed together with just a big mixture of other things that don't have any interest. But gold is in there. Precious metals are in there. Uh, there there is the potential for making money off of garbage, off of nuclear garbage or nuclear waste. It just requires a efficient separation technology to do it. And the efficient separation technology easily could be laser based. The problem is that it would probably also give an enhanced potential for misuse as a means of producing weapons materials.
Yeah.
Yeah, I've got Kurt Sorensen gave a lecture just on that, and he listed a whole bunch of all kinds of precious metals and
Mhm.
isotopes as well,
Mhm.
which could be gotten out of spent fuel. But like he was saying, like years later, I guess is in the process of breaking down, it breaks down into these metals, I think.
Right. Well, the other nice thing about laser separation, laser enrichment, is that you don't add other materials that get messed up and that increase the volume of the total waste flow, that's produced by your process. The laser separation doesn't necessarily have to add any mass to the material that you're actually separating, and it's a big benefit, minimizing waste streams when you're talking about radioactive separations, when you're trying to make isotopic separations and separate, this from that, the valuable from the unvaluable and all that. That's very attractive for laser separation. And
Hmm.
I think we would be going further. We would have already have gone farther with it if it didn't have the potential for misuse.
Yeah,
Yeah.
I think that's relatively true, but it does look like there is a Silex Paducah laser enrichment facility that at least was scheduled to become a pilot project around this time, around mid 2024, according to the earlier stuff that I covered. This was an article from last year, so projects a year out tend to be delayed, but it's certainly possible that we're approaching that. And so, what it sounds like is that we really need to be on the lookout for dangerous adversaries acquiring this kind of technology.
Is it classified?
Its existence or the technology?
Both, I guess.
Well, here in the Nuclear Engineering International magazine, the technology behind it, I assume, would be.
Yeah, I believe that at least it's proprietary. The
Yeah.
Silex actual system is a proprietary system, and other people like General Electric have worked on it and have supported the development. So all of the focus that I am aware of was with respect to producing U-235 or higher enrichment,
Right.
uh, you know, nuclear fuel. But it may have been actually considered for other tasks, which could be valuable with respect to recovering valuable precious metals and materials, in spent fuel.
Wow. Could
Hey,
terrorists get hold of that?
Yeah, well, that's the other worry. Actually, lasers are pretty inexpensive, and it, while the lab lasers were pretty big, uh, that isn't necessarily the only way that you can approach enrichment. So, you could propose, and once again, this is not my specialty, and I probably shouldn't go too far with it, but it's conceivable that with a relatively small investment, you could create a laser enrichment capability as a third world nation and potentially, either make a weapon or at least support some nuclear application.
Is the IEA capable of controlling this or monitoring this at all, or is it really the Wild West?
Well, they do a pretty good job, all in all, is what I would say, but the job gets harder over time. I don't really predict ultimate success in trying to keep nuclear materials out of the hands of people that shouldn't have them. People that we would prefer not have them. I don't, we've actually done pretty well for 70 years, but I don't think that will go on forever. The technology to do the work as laser isotope separation, other technologies, which probably are suppressed right now, probably are actually deliberately, chosen against, and funding and things of that nature to pursue those areas are probably deliberately suppressed. Uh,
Would it
anyway,
have,
mhm.
yeah, would it have to be a nation state that could only have the capability of creating a bomb, or could, let's say, ISIS
Mhm.
conceivably create such a weapon?
Well, if you reduce the cost and there were some source, like if I had access to, old 1950s spent fuel, that was stuck in barrels, steel barrels, and then dropped off the Farallon Islands or something like that. If there was a source of material and, I had a separation technology that I developed and worked that didn't cost that much, it might be less than $100,000 worth of laser, in order to build the separator. I could potentially, even if I was a Teamsters union, I might potentially be able to uh, build something that would maybe not be the ultimate yield, but it would be something to deal with. It would be a device.
Mm.
So the range of possible characters that could get involved in nuclear terrorism is wider than we have been used to seeing. And they're also the thing that almost all of our preparations have been with respect to examining the way that we historically developed weapons technology in the 1940s and 1950s. So we know how we went about it, and we know how we could have slowed the development of these technologies, but it's not necessarily true that uh, current nation states and terrorist organizations, they might not take the same approach that we took back in the 40s and 50s. And that is one of the concerns. We have a tendency to just really lock up on yesterday's battles and think, well, the only way to do it was the way we did it. And the truth is, by bootstrapping technologies, in particular, bootstrapping fusion and fission, it is possible to get new devices that haven't really emerged, from the traditional weapons complex. People don't necessarily have to do it the way we did. You can do it completely different way. And the materials that could be used to do that are not of the same grade or enrichment or anything like that we used, and that we set up all of our rules of thumb. The idea is to get as many fissions as you can in a short amount of time, to make a successful device. That's just kind of a basics. And if you combine fusion and fission using fusion neutrons to basically create fissions, fast fissions, or fissions, you can make successful devices that are very different from anything that we have in our arsenals.
Hmm.
Well,
And
go,
and
go ahead.
maybe a lot cheaper too, a lot
Yeah.
cheaper. So I don't myself have a lot of hope that we'll be able to keep these things under control by just trying to restrict access to fissile material.
Mhm.
I think that we will ultimately fail at that, and we will have to use a different approach to trying to keep proliferation under control. Here I'm way beyond, my competence and direct knowledge. I was entirely invested in nuclear testing and an underground nuclear tests at Nevada and the Marshall Islands. Actually, those were atmospheric tests. But long and short, these are design levels, speculations. It's just, I do get to talk to guys like Ralph Moore and others, and they are worried too, that the way we go about it today and trying to restrict access to fissile materials, it just won't hold up. It just gets the supporting technologies and infrastructure just make it easier and easier. And unfortunately, thorium molten salt reactors and lifters, they will have a real defined risk associated with them. And the only way they can be safe is to ensure that they are regularly inspected. And in particular, if there is a chemical support plant or anything of that nature, associated with the TMSR lifter, have to really go through that carefully, as that would be a very likely place where weapons material could be diverted and captured.
And let me take a tangent, very, very small tangent, to other breeder technologies, things like the EBR2 and other uranium breeders. Were these a greater danger than a thorium fuel cycle, or did they fail for another reason, and or did they just fall apart because we didn't want to spend money on nuclear energy?
I, well, I would like to let your readers know that I probably have a bit of a bias in this respect. And I think that most of my nuclear friends, are a lot of good guys, Rod Adams, a whole bunch of characters that I really respect. They probably have a different view on sodium fast reactors than I do. I'm pretty well known and criticized for the fact that I tend to oppose that technology. It's a technology that we've invested in heavily over the last 50 years in the United States. And some might say, looking back on it historically, all of the money went into this black hole and basically nothing came out, at least nothing after the EBR-2, which was actually a research reactor that came out of 1960s efforts. So everything from 1970 on basically went nowhere. We spent all of our money, literally every single R&D dollar that we could lay our hands on. It all went into this effort of sodium fast reactors. And none of it went into things like molten salt reactors, not past 1975 at least.
That's
The act
crazy.
Yeah, it is crazy because really our need today is not so much for nuclear technology to reduce, the volume and toxicity of nuclear waste. Nuclear waste is not really, I mean, we don't make that much nuclear waste in truth. You know, People talk about all the nuclear waste that we've generated since we started, the atomic age. You could put on a football field to a depth of about 10 feet and and house it all there. So it's not that huge an amount of volume. It's not that huge amount of radiotoxicity either. It's actually most dangerous when it's just produced, just removed from the reactor. It actually decays. The most radioactive components decay pretty rapidly to where after a decade or 2 decades, you're down to really low levels, overall. Uh, so the reasons for building sodium fast reactors uh, have been, in my opinion, overstated. To try to basically uh, address, a problem we don't have to historically address right now. The current mechanisms of cooling pools and casks and geological storage, things like that. We can basically leave to another day when technology is a bit better and more advanced. The actual uh, resolution of the nuclear waste problem. What we need today is replacement reactors, for the aging Gen 2 light water reactors that we're relying on for 20% of our power in the United States. We don't really have reactors that we want to build. I mean, there are some commercial reactors that have been designed, and they're basically just kind of linear extensions of light water reactor technology. But people in the United States are not enthusiastic about buying those and building them. And we really need better reactor technology. Reactor technology is already very, very safe, but we could take it another times 10, with newer designs.
Hmm.
And we
Maybe cheaper
should.
too.
Yeah, cheaper and better, safer, passively safe, walk away safe. All those things are described of new nuclear designs. I favor molten salt reactors. I do like them a lot. I think they have a lot of intrinsic safety features that make them the primary hope for the future. But
Hmm.
sodium fast reactors have the potential for creating large accidents. And even though they have actually a pretty good operating record, if you look at EBR-2, that was a very successful reactor project at Einel. And even there were 30 safety incidents that occurred during the 30 years of operation of the EBR-2. Well, most of those were small, like sodium fires. When you expose sodium to the air, if there's a little leak, it immediately just spontaneously catches fire. So most of those safety incidents were like that. They weren't like large releases and big meltdowns and, problems of that sort. But it's just to say that even the professional operators at Heinel, they didn't have like no safety incidents. They had defined number of safety incidents. If you look at the total radioactive inventory of a sodium fast reactor and the fact that the sodium coolant, which is a huge amount of sodium coolant, like a 1 gigawatt sodium fast reactor, cool style, modern style fast reactor, you could expect to have about 5,000 tons of sodium coolant in that reactor. All that sodium coolant. So the fact that sodium, when it comes in contact with air or water, immediately creates a fire, produces hydrogen, which can collect up at the top of reactor containment and detonate, not just burn, but actually detonate.
Are you talking about the fast reactors?
Yeah, the
Yeah.
fast reactors have a real safety hazard that is not acknowledged sufficiently. And I come from the standpoint that reactor development for molten salt reactors, but if you jerks want to take 100% of all of the R&D money for 40 darn years, an entire lifetime of an engineer within DOE, if you want to take it all, you're going to have to justify it. You're going to have to say, why, what did we get out of our past investment? And what are we planning to get out of, continued investment in this wacky direction?
Yeah.
And the truth is, you end up with reactors you really don't want to operate and build. I mean, if you let communities know the potential for explosion of 5,000 tons of, highly reactive neutron activated sodium, they would not want to be within 10 miles of your reactor. I mean, nobody in the right mind would. But, molten salt reactors are a different issue. They're intrinsically much safer. I personally would be willing to sit right on top of a molten salt reactor, and spend my senior days in nuclear warmth of molten salt reactor, right below me. But I would not have similar comfort sitting on top of a sodium fast reactor.
Do you have any closing thoughts for us?
Well, that's awfully kind. I think that it's easier to evolve nuclear technology than it is to invent it.
Great. So that's been a wonderful perspective from you, Robert Steinhaus. This has been the Ecomodernist channel live. You can find us right here every Sunday at 10 a.m. Pacific, 1 p.m. Eastern. You can find us on x.com at Carl Alex Pauls. Our primary channel is, of course, YouTube/Ecomodernist1. That's the Ecomodernist channel. And please support us on Patreon at the Ecomodernist channel. And remember, emissions first, peace and justice will follow.
Please subscribe to us on YouTube, Ecomodernist channel. Also to subscribe to us on Twitter and Facebook, Ecomodernist Society of North America.
And online at https://esna.earth.